for Machine Learning on Finance. Our first speaker leading off the event is Anastasis Kratsios from McMaster University. Anastasis develops and studies universal deep learning models that leverage geometric structures in mathematical finance and data science problems. His primary focus is on developing the foundations of geometric deep learning as it pertains to stochastic analysis. He's primarily working on the approximation theoretic and statistical learning foundations of the models he and his team develop. Before joining McMaster University's mathematics department as an assistant professor in data science and mathematical finance, Anastasis did his postdoctoral fellowships at ETH Zurich and at the University of Basel in the mathematical finance and computer science groups, respectively. He did his PhD under the joint supervision of Cody Heinemann and Alina Stanku at Concordia University in Montreal, working on the geometric approaches to machine learning and finance. And today he's going to be speaking to us about efficient approximation of infinite dimensional dynamical systems in finance, from stochastic filtering to adapted optimal transport.
Well, thanks for the really nice introduction. And yeah, I tried to compress this as much as possible, and that's what we have. So today I'll be speaking about precisely this, and what I'll be talking about is joint work with a few people. So it's mostly based on two papers, though of course influenced many others. So the co-authors of the first part of the talk are Luca Galimberti from who now is technically University of Norway, and Giulia De Vieri, who is in the Scuola Normale di Pisa, and then Beatrice Acciaio and Gudrun Palmer for the second part of the talk, and they're at ETH. All right, so the structure of the talk is like this, right? So I'll just try to introduce and motivate this slightly different, but not so different perspective on machine learning and finance. So motivation. Then we're going to sort of cover the so-called linear case. By the linear case, I mean, well, you'll see not that the functions we'll be looking at are linear, but rather the spaces are linear. And then we're going to go to sort of a nonlinear, sort of geometric deep learning type setting. Yeah, that's the evolution of the talk. Okay, so yeah, so to motivate things, let's just start off with, I always like to start off with some like sort of philosophy or something. So in mathematical finance, what are we usually interested in? We're typically interested in, well, getting predictions, right, from functions which causally map, so sequences of inputs to sequences of outputs. I'm usually thinking discrete time for the moment. And just to look at that, what does that look like? Well, if we just stop at a moment in time, t, so for a second, t is going to be an integer, that function would take our time series up to the current point, so xt, and then say yesterday, the day before, and all the way to the infinite past, as much data as we have, and then make a prediction based on that. So inputs are time series from now, yesterday, the day before, infinite past, and the output is something, so say yt, right? And sorry. And because our, I guess, causal map, as we want to call it, is a function that does this, and it sort of takes sequences inputs and sequences outputs, and at every single point in time, it looks like that. So there you go. And we're going to just make one convention in the talk. In general, when you hopefully read the papers. Okay, so is that T0? So I think there's a bit of feedback on the mic. Yeah. Sorry, I'm going to move the mic. Or maybe it's this. Okay. I was rubbing against something. Okay, that could be it. Okay. Yeah, so the time 0 is always going to, I'm going to think about this as now. This is the, do you also hear some feedback? Yes? I definitely heard. Yeah, I also. Still wearing yeah. I wasn't sure what you put down. No, I put down the, yeah. Oh. Yeah, let me just move it slightly lower. Ah, okay. Technical difficulties. Okay, so now we did some denoising. All right, so for now, in the talk in general, time, at the current time, it's always 0, okay? And all the negative time sequences, which maybe is like, some people have maybe seen a bit less, that I'm thinking about as the past. This is yesterday, day before, all of my past data. And of course, positive times is going to be denote the future, all right? So that's what we're typically interested in. So I'll give two sort of motivational examples that kind of will by no means are exhaust what we can do, but I think kind of motivate and capture many of the essential ideas of the first and second parts of the talk. So in the first part of the talk, we're so-called the linear case, we can motivate it by the following problem. So oftentimes in mathematical finance, or more generally in stochastic analysis, you want to describe some evolution of some model, some process, but you don't have full information over it, right? So in this case, the stochastic process we're looking at is xt, and I just give it as this for simplicity, but it's not required, as a specific stochastic integral like this against some predictable process beta, right? And just imagine that this model is provided me by an expert, okay? So imagine I want to trade, and I need to know xt. I don't actually know xt. I have some partial information. I'll describe this in a moment. And there's many, say, quants who have many more years of experience trading than me, and they all have different opinions about how this process should evolve. And one quant, for example, for this slide says, okay, the model looks like this. This is my input to my deep learning model is an expert's model, right? So for example, like this, right? And this person is modeling a not fully observable asset or some other financial quantity. So suppose you have a subfiltration G of the one generated by X, strict or it's not so interesting. And what we want to do is at every single point in time, we would be interested, if we're discretizing time, of course we do, we want a map which takes, in this case, which takes the current state of the process xt at every single time, and the previous step on a discrete time grid of size delta. I don't know why it keeps flicking, right? Here. And the previous time before that, so t minus 2 times delta, and so on, so on, so on, and then produces, so since this is a Markovian process, we really only need to look at this, and then look at the conditional expectation of my process given the information I have currently in my sigma algebra GT, right? So in other words, what does that mean? What am I talking about? So I'm interested in sort of an operator which takes sequences, so sequences of the historical evolution of a model provided to me, and then tells me how that model would conditionally evolve under my limited information, right? So inputs are models given by experts, outputs are what that model would look like under partial information, and I want to trade onto that, or whatever. Okay, so of course, this is that causal in the sense of the last slide, but here is another example that is somehow completely different. And for simplicity, again, I'm going to consider stochastic differential equations and just suppose it's given like alpha and beta are the drift and volatility or diffusion, and there's some functions such that this makes sense as unique strong solution, whatever. But the most important thing is the input-output system that I want to study, right? So inputs, so I'm just going to compress notation a bit now as the following. So in this case, I'm going to consider I'm at time t. I've seen the path of my process, right? So you see this, your stochastic, the model you want to add, the quantity you want to model, so a stock, a bond, whatever. Well, maybe you don't know what happens in the future. Maybe you'd like to understand its distribution of what's going to happen in the future, right? But you definitely have seen what's happened right now and in the past. So in this case, the sequence that's being fed to my model is the actual realized path of whatever I'm trying to model. And the output at every single time is the conditional evolution of, say, my asset. So it's the conditional distribution of x, t in one type step in the future. This is delta, so t plus delta, conditional on, this is Markovian for simplicity, on the current state of my process is xt. Of course, I want to highlight one thing. None of what I'm talking about in the paper needs to be Markovian, but I'm just putting the sequences here just to remind us that in this example, things are Markovian, but in general, we always think of sequences of arbitrary long memory. Okay, but another example here is maybe I have something more sophisticated to do than predict one step ahead. So another example in the same vein, suppose you have this stochastic process, and then what I want to do in another variant of this example, so just illustrating the causal maps in finance, is, well, again, my input sequence is the realized path, and my output sequence now is for every single time t, I give, for example, the conditional distribution of the next 10 time steps. Okay, so the joint distribution, so this of my stochastic process in the next time step. So t plus delta, so it says 2 delta, t plus, say, for example, up to t plus 10 delta. That's this joint paths evolution and conditional on, for example, since it's Markovian, the current would have actually just observed in the current state. So x process is right now little xt. Okay, so in both of these cases, we have inputs, so maps that take sequences of inputs and map sequences of outputs. And the main thing that's important about them is that they're causal. And by causal, I mean the following thing is, why is causality important? So causal is I just mean that it's any function that's not looking into the future to make a prediction about the present, right? And from a machine learning perspective, the causality is important because even if we'd love to have like non-causal functions that are used, so that would be, say, for example, a function that maybe wants to predict the price of a stock tomorrow, given how it's going to behave the day after and right now. Yeah, those functions exist. That's great. But the problem with it is that, from a machine learning perspective, is that you can't actually feed inputs into those functions, right? So even if those functions exist, we can't evaluate them because we don't know one of the inputs, which is the price of the stock tomorrow. So in some sense, you can think of causality just being like, this is the only things that actually are evaluatable in practice. Okay, so the goal. So the goal overall of this type of philosophy, which I'll be explaining over the next bit, is we want to design a deep learning framework for making optimal, and I'll explain that in a moment, causal predictions. In case I'm always highlighting the keywords, using the fewest model parameters. Okay. Okay. So how to go about that? Well, there's a few different ways, but so motivated by sort of the recent success of deep learning or machine learning in general, but really deep learning, someone can suggest, well, we can use a deep learning model, right? And so here I have a nice sort of pictogram of some deep models that came to mind that are particularly nice, and how sort of they're organized, and sort of this brings us to our first problem, right? So here, let me just explain part of this deep learning landscape. So there's some feed-forward type models, right? So feed-forward networks, convolutional neural networks, sirens, flow-based networks, whatever. So geometric deep learning models. So popular ones are sort of graph neural networks or graph attention networks. Then here, there's some neural operators. Those are models that work between infinite dimensional spaces. Yeah, I should say something here. So of course, I'll go into some detail about each of these, but at a high level, these are models that sort of respect the geometries of their input-output spaces. Typically, graphs are studied. Right, the sequential deep learning models is probably one of the ones that may be more familiar to everyone in the audience, besides feed-forward. Yeah, and so examples are recurrent neural networks, residual neural networks, or GRU-based models. And of course, another very popular branch, which is very different, is the extreme deep learning models. So those are models whose sort of parameters are all random, almost. So typical examples that really get the point across by the name is random feature like networks or random feature models or reservoir computers, right? So the point is there's, of course, a huge plethora of possible approaches or tools at our disposal. But what I want to tell you is that none of them really gets the job done, okay? So why not simply use one of these machine learning models and call it a day? Is this talk only about applying some package in Python? No. So why not use one of these pre-existing models? So many of them after all. Well, because those models simply don't capture, nor do they preserve, the relevant structure in these mathematical finance problems, right? And the main word that I want to highlight here, so kind of the main point of the talk and also probably the main point of my research at some level is the keyword is structure, right? There's some structure that's just not being captured. So in the first part of the talk, so if you notice this little pictogram here, there was sort of two empty intersectional spaces. Those right here and right here, now there's some blue dots. The first part of the talk is going to be talking about, I would want to call it a model. I'd rather think of it as a modeling framework. It's way too general to be just a model, way too flexible. So a modeling framework that's looking at the intersection at neural operators. So neural operators is the neural network approaches to infinite dimensional learning, if you will, linear. That's the name of the first part of the section. Yeah, and then the second is sequential deep learning models. So there really isn't anything really there, at least nothing with theoretical guarantees. Right? We want to know that our model is doing what we want it to do. And then the second thing is, so it's something that's lying at the intersection of geometric deep learning and sequential deep learning models. And that will be motivated by the second part of the second problem, but I want to get to that one when we get there, one step at a time, okay? But in a nutshell, the main point is that we're going to be thinking about things that are evolving causally, so sequentially and causally, but they also encode some nonlinear structure in terms of input-output spaces, right? And so that's where this second part is going to be. Okay. So problem one, let's just return to it with only a tiny bit more detail, but not too much. I think understanding the problem is the most important part. Okay, so problem one, we want to understand this intersection between neural operators, so learning on infinite dimensional spaces, and of course, sequential deep learning models. Right? So I'm only going to put a bit of notation. So suppose we fix a stochastic base. So it's the filtered probability space, some nice properties, and so that's where all our stochastic processes are going to be defined. And then we're just like in problem one a few minutes ago, we fix a subfiltration, right? And this captures all the information we have, right? So this problem is in any way interesting, we imagine the subfiltration is strict, right? I always feel like I have to say that. Okay, so I'm just going to try to visualize everything. I mean, this is how I usually do things in my mind, but less pretty. So the problem that we're thinking about is we want to learn this, which I'll explain. I'm just not going to put it on the board and expect everyone to read. We want to be able to approximate, or at least approximately implement this this operator, right? So this operator, what is it? Like, what's going on? It's doing the following thing. So on the slides, I'm having I just want to make one technical point here. On the slides, I really wanted to emphasize that in this line of work, though I do work in discrete time, the time to discretization could be arbitrarily small. So I'm just going to put the delta here and think of this as some positive number, right? But when I'm going to say it out loud, because it's going to be very tedious to say t delta, 2t delta, 3t delta, I'm just going to say, I'm going to imagine delta's 1, okay? But just keep in mind, when I'm saying it, just because it's just a mouthful. Okay, so that technical comment aside, we like to learn this this linear operator, and what is it doing? So it's taking inputs, sequences. So it's better. I think it's better to read it here than go up after. It's taking its inputs, which are really the models, or rather the evolution of a model, right? Viewed at discrete times. So time 0, time 1, time 2, time 3, or like based on my comment, 0, delta, 2 delta, so on. And then at every single point in time, it's saying how that model, so that expert's opinion really, that model would behave under the partial information available in our filtration that we're giving it, right? So GT. So in other words, we're just evaluating, we're taking a sequence of, taking a model, looking at sequence of random variables that's sort of describing its evolution, and we're conditioning that, we're projecting that down into our space of less information, right? So a bit more formally, what are the inputs and output spaces? Here, I think this one's quite important, this example, because it illustrates the following thing. The input space is it's a product space, right? And at every single point in the product, where I'm just going to omit negative times for simplicity of the talk. For every single point in the product, we have assuming some square integrability of all these models, we have all the random variables that are square integrable and are measurable with respect to our complete sigma algebra at that time, right? And so I pick the product of all of these, and my point here is that just keep in mind, notice that the stochastic process, it's somehow encoding its adaptedness, like you might usually describe in the classical terminology. It's just really saying I'm giving you a sequence such that it lives in this product space, and and the products are sort of the filtrations evolving over time, and the output is then the following sequence I described, the sequence of conditional expectations, right, for that given input. So and this one, of course, lives in this product space also, right? And the interpretation here is adaptedness, right? So this sequence, if you're looking at every single index, it's, of course, adapted by construction, but also my point is everything living in this product space is adapted to the G filtration, where every single time you move along a coordinate, you're sort of moving to the bigger, the L2 space on the slightly bigger signal algebra, assuming you're getting some information at some point in time, right? Okay, so so this guy here, once I fix my filtration G, I'm just going to give this function a name, and I want to learn this function basically. So this function, this operator, I'm going to call it filter G, because this is a really stochastic filtering problem in some sense. And what's going to go into it, I'm going to visualize it here. The inputs are model experts' opinions of the stochastic process, which I'm interested in, right? So one expert, for example, might say, okay, xt looks like this. It's just for simplicity, say it's this martingale here, integrated against this alpha process. And other experts say, no, it's actually integral against b, beta, gamma, delta, and so on. And of course, maybe I'm interested in any sort of possible convex combination of these. Though in the paper, I just want to emphasize, or in the theory, I would say the paper, in the theory, you can have arbitrarily many experts, right? The point is that I have some inputs, and these are all sort of viable models, and I want to do this important thing. I want to, with a single neural network model, learn how to filter all these models, right? So then, given any expert model in this blue square, so anything that's viable, I want to say, here's my single deep learning model. I can at once apply this to all of these guys. So one model, so one neural operator, if you will, for all these models gives me a host of solutions to all these stochastic filtering problems, right? So each input sequence is a model, each output sequence is a solution to a stochastic filtering problem, right? So yeah, so my goal is to approximate this operator, filter G, or I'll call it filter for fastness, as efficiently as possible using a single model, right? It's a single neural network model for across this entire mixture of several experts, right? And why, just to reemphasize why this is, I guess, why this is important, it's because here I've implicitly been putting my robust finance hat on, right? So of course in robust finance, I like maybe more classical mathematical finance, or we typically think, or actually we accept the reality that all our models are wrong. And so maybe if you want to make predictions, it's better to look at an ensemble of models. Maybe you care about the worst case behavior from those models. It's very classical, or some other statistic of these joint ensemble models. So here, I'm really thinking robust finance. I accept that I don't know what's going to go on. I also believe that all my experts who are in my company who I've hired are good enough to maintain their jobs, so they all have good opinions. So I want to basically make my decisions based on all of their opinions together, right? So I want a model that can treat them all in one shot, right? Okay. So that said, what do we know about this filter operator, right? Okay. So examining this filtering, so this filter operator, let me just say one thing, is going to sort of, it's pretty much almost a prototype of what we can treat with the first theorem when we get there. So let's just think about what it's doing, right? So the first thing which I've really hammered through in the last 25 minutes is causality, right? Clearly the output of this, so for any input, which again is a sequence, the evolution of a model, right? You give me a model and then give me its evolution, and I want to predict to you its stochastic solution to stochastic filter. I want to filter this thing basically. I want to compute the sequences of conditional expectations. The most important thing that's what to think about it is that at every single time t, or like delta t, right? The output at that model at that time doesn't depend on the future. It only depends on what I've seen now and in the past. Right? The second thing, which is a bit more subtle, and I'd like to motivate for a second, is that this this operator is in a sense smooth. Okay. Now, why will that be important? Before I describe what is smoothness, let me just think about like R, functions from R to R, right? So of course, I want to approximate things. I'm always using the word approximation. I'm kind of getting that into the talk. So, okay, imagine you want to approximate a very smooth function in one dimension. Of course, it's very easy to do this. You don't need a very complicated model. You just be able to understand like a few things, like its first few derivatives and so on. You can kind of get an idea of where it's going, its shape, and so on. So somehow the idea is that very smooth functions should be easy to approximate with like very simple models. Right? On the other hand, imagine a single realization of a Brownian motion path, a typical one. It's something very rough, and even the approximations we see on our computer, it's bouncing all over the place. So if you want a good approximation of it, then we need to capture all those inflections and all those bounces. So that means that a model that should be able to approximate a low regularity object, a low regularity map, should be very complicated. So right now I'm pointing out that this model is in a sense smooth. And what I mean by that, I mean, this is a really smooth function. It's the following things that when I consider the outputs, so what it's doing at every single given time delta t, in this case it's rather simple, it's just a continuous linear operator, a bounded linear operator, right? So of course, this is differentiable in a certain sense. So differentiable in the sense of all its directional derivatives in the infinite dimensional sense, but it's also differentiable in a slightly weaker sense. That's enough for the paper, but just imagine this. Of course, anything linear is probably smooth, and continuous and linear is probably smooth in our traditional sense, right? So the most important thing is that first, the structure of the function itself, not thinking about the spaces yet. Yeah, it's causal. And the second thing, it's super regular. It's as regular as it can be. So it's a smooth function. So it has all its directional derivatives and higher order versions of these. Okay. The second thing to notice is the structure of the input and output product spaces, right? So in this case, we have these infinite, one thing at a time. We have linear metric spaces, okay? So by this, I mean both spaces, we have a distance function on them, and they're vector spaces, and yeah, there you go. Their topology is generated by that distance function, yeah. And in this case, I mean, I chose this example particularly because it's super nice. They're Hilbert spaces, and they can't get much nicer when you're in point 2, and point 2 is infinite dimensional. Right? Another thing we should observe about this, which really will change how we solve the problem compared to more classical approaches, they're infinite dimensional spaces. They're genuinely infinite dimensional vector spaces, and so keep this in mind, right? And the third and last point, which is a technical point, but it's super important in constructing the part 1 type solution, is that they all have a notion of a basis. And by this, I mean they have a functional analytic basis. So I wrote the words in gray for those who just want to say, okay, they have a basis. But for everyone who might care, this is so they all have a Schauder basis, right? In other words, what does that mean? It means that every single point I can sort of asymptotically, uniquely write down as a certain sequence of coefficients, if you will. And in this case, it's really nice. I think it's a really nice connection to classical, semi-classical things. In that case, the basis is given explicitly by the sort of Wiener chaos, right? So these are iterated integrals, or the specific Bayes, Wiener chaos and basis together is Bayes apparently. So the specific basis that I'm thinking of is iterated integrals of, if we're working in one-dimensional stochastic processes, of just the Fourier functions, right? So this will give me an orthonormal basis and a particular Schauder basis of each of these spaces. And when I product them together, this is definitely not, the product space itself is obviously not a Hilbert space, not a Hilbert space, but it is a infinite dimensional linear space with a metric. And yeah, by just combining these Wiener chaoses evolving through time in an obvious way, which I'm not going to get into, you get a basis for each of these infinite dimensional spaces. Right? So the point is, both input-output spaces are linear metric spaces. They're infinite dimensional, super important, but we can approximately implement all their elements because in a unique way, because they have Schauder bases. And in particular, we know the Schauder basis. Okay, so what is the solution to our problem starting to look like now that I've kind of described the problem? So I really am a big fan of pictures. So this is a pictorial description of the solution. Right. So things to decode this picture with, right? So inputs are coming from the top, outputs are going at the bottom, time is flowing diagonally this way, okay? So here, for example, every single little bubble, just imagine this is a stochastic process. I just depict this as a squiggly line. I think this is a reasonable description. And the output is also, for some reason it's rough, but it's a squiggly line. Okay, so every single point time t, a model comes in. This is one of my experts say, hey, this is the model that's modeling xt. Listen to me, you know? And so, okay. And so my process, so my model, which is abstractly at the moment, given by these yellow square things, we'll take that person's model and make a prediction. This prediction is the conditional expectation of that model given the information and time, say 0, for example. Okay. Then, right. Next, what happens? Well, if you think about the problem from the last slide, I'll just flick back. You notice that one slight, subtle but super important thing is happening is that I'm also gaining information, right? So I don't want to apply the same. So if you just remember in L2, the conditional station is an orthogonal projection onto the subspace generated by the less information, right? So G0 at time 0, right? So what happens is I've gained more information, so I don't want to. So if one of these yellow blocks is approximately implementing that projection, the subspace of less information, I don't want at the next time step to project in the same space. I've gained information, so I should update, right? And so I'm changing color because I'm updating here. But what's happened is I want to update the internal parameters of my model so that I'm approximately projecting onto the information of the subspace in L2 of G1, for example. This is the next step in my filtration, and so on and so on and so on. And how do I make these updates? So this is the one part I can explain very quickly. I think it's really, really nice. Before I explain how these blocks work, this is a bit more complicated. The most important thing to say is that they depend on finally many parameters, of course, or else it wouldn't be feasible. But we update between these blocks by updating the parameters, and that update is kind of very nice. What you do is you have a sort of auxiliary neural network, which in the pure machine learning literature, there's pretty much no guarantees theoretically on this object yet. It's up and coming until some of these two papers, basically. So what this hypernetwork is besides having a very fancy name, it's a neural network who takes inputs and produces outputs a neural network, right? So, but more formally, you're taking the parameters that are defining this neural network. So it's a neural network defined in the parameter space of this neural network model, which I'll explain in a moment. It takes the parameters that I have at time 0, and it predicts the parameters at time 1. In other words, it really predicts the next neural network, right? So and the same thing, time 1 to time 2, time 2 to time 3, and so on. So in other words, the hypernetwork, said mathematically, it's a dynamical system defined on the parameters, in the common parameter space of all these infinite dimensional neural network models, which I'll describe to you in a couple of slides. And that dynamical system is implemented by some type of optimal neural network. So it's like a higher order neural network, right? Okay. So this is just a classical feed-forward ReLU network, which I still will do a review of. But the point is that somehow this object is classical. I just use it in a very cute and fancy way. But the main mysterious bit is what is going on here, right? So how do we go from random variable inputs to random variable outputs? Because we know how to chain them together now, you use this hypernetwork, right? So how do we go from infinite dimensional inputs to infinite dimensional outputs? Okay, so to explain that, since of course after all it is a bootcamp, I would like to do some review. So the proud thing about COVID in the last few years is that I've always been speaking quietly on my computer, so I'm starting to lose my voice progressively. But it's okay, I'll use my inner Greek and I'll get louder. Okay, so to explain that model, okay, these vertical arrows, which we'll give them a name now, so I have a name in mind. They're called neural filters. You might see here. We need to understand the first basic building block, which is sort of the most standard, the simplest neural network model, right? And let me just say one thing. So the feed-forward neural network, which is the thing I'll be describing in a second, is sort of the most classic, most simplest neural network model, but it's also the one that we understand sort of the best in theory. So my point is that if you're caring about the theory, let's chat, we'll do whatever. But if you're caring about the practical implementation of this beyond theoretical guarantees, then of course you can swap the feed-forward network model for some other network model, which you deem more appropriate for whatever insight you have from a specific problem, right? But for mathematically, this is the simplest to understand and still only being understood properly as this year, I guess, and not even. So let's start like that. So our basic building block is the feed-forward neural network. So what is that? So feed-forward neural network is a function from two Euclidean spaces, our little d to our big D. These are both positive integers. It has a very computer sciencey flavor. It's defined iteratively by doing one procedure many times, right? And what is that procedure? The procedure is composing a sequence of functions, And each, so as you see here, from this side to that, we're doing a composition of functions. Each of the W functions are affine maps, so just linear map plus a shift, right? The only thing I'm assuming is that these are composable, obviously. And then between each of these affine maps, I'm truncating the negative values. This is a simple example of a neural network. So ReLU neural network, right? So every time I apply an affine function, I have a new output, and that output I coordinate-wise, so this is the black dot, I truncate all the negative values. Oh, thanks actually a lot. I guess it's obvious that the voice is getting raspy. On that note, another thing I learned during the talks is just hydrating with coffee is a bad idea because then the speed really diverges. So thanks. Yeah, so then I also compose with this univariate function that just truncates the negative values. And to make sense of that, because of course these are at every single time step you potentially have multivariate outputs between layers, right? Layers every time you use an affine map. I component-wise apply the sigma, and by that I mean I take any vector and apply, well, this univariate function to each of its components. Right? So affine map, component-wise application of sigma, done ad nauseum, j times. J is so-called depth of my neural network. This gives me a deep neural network from RD to R big D with depth j. Okay. Okay. So besides looking cool, and you can clearly write this on a computer with a loop. Why do we care about these? Well, one reason we care about them is the base level is their approximation properties. There's many other reasons. But since this is what we're talking about in the talk, I'm going to focus on the approximation theoretic properties. So first thing we know, so this somehow goes back to the late 80s, but really I think it's only properly understood this year. It's a very nice paper by a long list of co-authors, not of mine. So basically the idea is that for any continuous function, right, so the same domain and codomain, so from RD to R big D, I can always approximate that as to arbitrarily precision uniformly. So I can uniformly bound my worst case error on any compact input space, right? Input set. So you give me a compact set of inputs to my neural network, and I say I care about approximating my outputs for these inputs, and so-called universal approximation theorems will those say that, well, for once you fix the set of inputs you care about, as long as it's compact in RD, and you give me your error quality, so epsilon bigger than 0, I can find a neural network which is epsilon close to it uniformly for all my inputs. In other words, I can, in some sense, approximately implement any continuous function. Okay, but you know what? That by itself, it's not really fully interesting, I think, because you can easily write down many different classes of functions that can do this, but are not feasible in practice. So the main kicker on the approximation theoretic side is how this gets combined with the second thing, which is that neural networks are optimal in this sense, right? In the sense that they use their parameters as efficiently as possible. And what I mean by that, I mean there's certain sort of theoretical lower bounds for any model that's, okay. So given any abstract model that has a certain level of flexibility, so-called VC dimension, but I'm not going to go into this in the talk, I'll just say it in case anyone's interested. You can quantify how flexible a model is with a given number of parameters, and there's theory, there's classical, very classical theory that says that the best you can do with the model with a given flexibility, with a given number of parameters, is some rate, right? And you cannot approximate more accurately using that number of parameters and that flexibility yet. No, you just can't. So the best you can do is, if you're lucky and you model properly, you can achieve that optimal rate. So neural networks are nice because they can model everything, yeah, but they can do so as efficiently as possible. As possible, so using a given number of parameters, they achieve the optimal rate given by sort of classical VC theory. So they're not only universal, that's the first point, they're also sometimes they're optimal, right? So that's what we care about them. They're the best we can do if we don't know anything else about our function, rather besides it being continuous. So I always use the clicking with my hand. Okay, so that's neural networks. Now, what about neural operators, right? So what's a neural operator? It's a quick refresh. It's a neural network type construction between infinite dimensional spaces. Okay, and let's, before describing our construction, our framework really at this will be in a moment. Let's just describe what's been done. So neural operators have really caught the attention of, I think, people specifically in PDEs and I guess computational physics recently in 2017, late 2017. So that the first breakthrough model was so-called Fourier neural operator. So I'm going to put the names in case someone's interested. Long story short, that came out in 2017, and guarantees I think came out like last year, but the people in the applied math group at DTH. And basically what that is, it's a certain model that's designed to take inputs in the Lebesgue like L2 space on R, right? The classical Euclidean integrable functions, square integral functions, and produce outputs like that in some universal sense, okay? So there's a qualitative universal approximation theorem proven. And that's what's known about infinite dimensional learning at first. And then there's, of course, some other models that came along. So neural operators typically in the literature will refer to operators, nonlinear operators that are implemented by some type of neural network. And typically take some kind of function input and produce a function output, right? So they're usually people who in this literature are interested in, yeah, things like that. So maybe some inputs from a Sobolev space or a base observation like this, right? So it's always some inputs, functions on RD or something, and outputs on function on R big D. But in general, there's been some recent progress, to be honest, in the last few months beyond that front. And these are mostly for specific, with one exception, which I'll mention actually is one of the co-authors, it's actually how we met. With one exception, which I'll say last, even though it's listed first, they're mostly describing specific operator type networks for specific problems, right? So this one here just came out a few weeks ago from people at Singapore. I forget which the name of the university, so hopefully they won't. They've said if they're online. Yeah, I don't remember it's which one is this NTU and there's NUS. So just cancel where they are, but it's by Ariel Neufeld and Philip Schmucker. So this I know. So they're talking about approximating functionals of stochastic processes. So this is infinite dimensional input, real value outputs, and the motivation is for pricing, option pricing, right? Second one is by Cristo Cucchiaro et al. And this second one is again a qualitative approximation guarantee. So if you view a path of a stochastic process, you then want to price a functional of it. So inputs are paths, outputs are real numbers, right? And in general, there's been some qualitative approximation guarantees for inputs between, we'll just say Banach spaces plus, okay, so inputs in Fresher space, outputs in Banach space. But these are all sort of qualitative guarantees. Yeah, that's it. And these ones sort of deal with specific cases and really understand those, right? But overall, many things that remain open. Yeah, many things that remain open is how do you do this properly in a sort of principled like framework-like way. So if I give you my mathematical finance problem, I want a framework that automatically designs a neural network with these types of guarantees. Moreover, I want, like just kind of mentioned this in the last slide, I want that this framework produces a model which is not only universal, like in these qualitative senses, but I want to just achieve the next step, and the next step is that it should be optimal. So I want a neural network model to somehow, you cannot get more efficient, right? As you can give a number of parameters. So now we're going back to the neural filter, this orange box that I was pointing at with my red pointer. So a neural filter is a neural operator in this, taken in this abstract sense. For any suitable good linear metric spaces, I don't want to give too much technical details, but just probably most spaces almost anyone was interested in that's linear. With the only technical detail I have to mention, because it's critical for the construction, is they have a shadow basis. So you have a functional analytic basis. That means every element I can associate to it a unique sequence of numbers that somehow asymptotically weight some basis vectors in a way that I can reconstruct it uniquely, right? So it's like asymptotic basis. And now I can finally write down to you what that little yellow box look like. It's relatively, I think, intuitive, and it has three sort of steps, right? So this is why the basis is important. So first, you have an input in this infinite dimensional linear metric space with shadowed basis. The basis elements are going to write EI. So the inputs, because I have, so it's just a power series like this. I just wrote, yeah, I'm not going to write my summation from 1 to infinity, just a bit too tedious. Also, if I want to deal with finite dimensions, it's annoying, so I just put summation I, right? So any of these elements I can uniquely write down as such a Power series, potentially just a finite sum. And what the first layer does, so-called encoding layer or projection layer, you might think of it, it just truncates the basis expansion and gives me the coefficients of the first n basis vectors. Then, very simple, very super intuitive, I think, really. This is treated as a vector. You pass it through a feed-forward network. So remember that's you apply a linear map, then after you do that, you affine or just affine and ReLU function component-wise. Do it again, affine function, then ReLU function ad nauseum j times the neural network with depth j. One more affine function without ReLU, and then here comes my output. So my output is now in Rm. Okay, and the output now I interpret that as the coefficients of my Schauder basis, my functional analytic basis for my output space, and I just reassemble them. Okay, so this is a comment for the people familiar with the Wiener chaos. In other words, here I'm looking at my Wiener chaos expansions coefficients. I pass those through a feed-forward neural network, and I just reassemble them into the chaos expansion of the other output base. So it's beautifully simple, and that's the goal, I guess. So the decoding layer, right? So now I want also make one more comment before I get to the next slide, because this is the theorem. There's two types. You might notice there's two types of error that are going to be happening. There's the error, assuming infinite dimensionality, obviously, because our examples are infinite dimensional. There's the error you get from truncating the basis, and there's the error you get from somehow reassembling a function using only finitely many terms in its power series. So this is sort of dimension reduction error, or as we call it, encoding error. And there is, of course, an error that's coming from approximately implementing the function you want in the middle using a feed-forward network. You can only do so approximately. So, okay. So first theorem, I try to keep the theorems in the presentation sparse. There we go. So I always say good metric spaces, and sometimes I keep it in my slides, and this is one of those times. So given any Fresha spaces, so I think of Euclidean space, think of Hilbert space, think of Banach space, but imagine thinking you have something that doesn't have a norm. You can go that far. Beyond that, I don't know if anyone is too interested at the moment. So given any Fresha spaces, just linear metric spaces, really. And they have a functional analytic basis, so Schauder bases. My inputs are E, my outputs are B. Right, now given a potentially nonlinear operator, F, from E to B, and given a compact subset of E, those are the inputs I want to approximate my nonlinear operator on. So in the last, earlier, if these are my L2 spaces at a given time, this is the collection of expert mixture models I'm looking at, but it could be, of course, a mixture of infinitely many experts, so it could be really quite broad. Some technical condition about having at least 2 points in the set. Now I'm just going to assume some regularity of my function. So there you go. So I'm going to say either the function is smooth, or smooth trace class if you're familiar with that, or it's holder. We'll hold the trace class if you're familiar with that. Trace class, I just mean that the function either is smooth on the entire space, or it's not smooth or holder on the entire space, but it is on its little compact set, and it can be extended potentially to a different function, which is smooth. So that's kind of important. So just imagine the indicator function. If I'm looking at indicator function, this is clearly discontinuous. But if I don't care about approximating near the jump, that thing is smooth, right? So that's what I mean by trace class. So it's essentially discontinuous functions are included here, but they're almost smooth or continuous or holder. So can do these any such operator. Then for any encoding error, so this is my dimension reduction parts of my network, and for any approximation error, so epsilon d, epsilon a, there's a neural filter, the model I just described to you, that gives me a uniform approximation bound. So the distance function on B is dB. So for inputs, I can uniformly control the gap between my model and the true function evaluated at the point of interest. That's say expert mixture, and that's upper bound that's controlled by the dimension reduction error and the approximation error, right? So in other words, anyway, that's basically the theorem, right? So this is the qualitative part of the theorem, right? I didn't tell you how complicated this model will be. For all you know, this model may have so many parameters that the world's computers are not enough. So here comes the quantitative part of the theorem. So the quantitative theorem is, of course, this gets into the bound, like the region of numerical analysis. So I'm not going to write down the rates. The rates will like make everyone cry, including me. I mean, if you're as sensitive as me. So I'm going to give you the takeaways because that's really the gist of it. The gist at the first level. The first takeaway is, are the rates that we get, whatever they are, looking reasonable? So the first thing is that, okay, we're going to think of the complexity of a model in terms of depth and width. And here I just want to extend the notion of depth and width a tiny bit. So typically width of a neural network is the codomain of the affine maps that we use to build this iterative affine map for a loop function, affine map for a loop function. So it's how, in other words, is how at every single loop instance in our loop, how many vectors do we have to stir, right? So here, since we're first projecting and then reassembling infinite dimensional objects, by here I mean the width is also keeping in mind how far we projected down, right? So the first thing is this, is that the complexity of our model in terms of the number of iterations of the feed-forward network, the width, so the number of vector, the dimensionality of the vectors that is stored in every single iteration of that neural network model. I don't know what to do. Let's see. Great. That was easy. Okay. So yeah. So the. Oh my gosh. It's. All right. Cool. So now I'm very aware of what I'm saying. Right. So the model complexity will increase as the error decreases, right? So error, I'm just going to write epsilon for approximation error and dimension reduction error together. So if I want to have very good representation of my inputs and outputs, low dimension reduction error, and I want to have low approximation error, then of course I need a lot of depth. I need to project onto high dimensional spaces. So my depth on my feed-forward networks can be large, and my widths can be large, and vice versa. If I want a bad error, then I don't know how to turn this off, honestly. Yeah, whatever. Yeah, it'll take too long to debug. So yeah. So anyways, there you go. Okay, so then that's the first thing. The second thing is that how does my model complexity just behave with my inputs, number of inputs I care about? So say k is that compact set, and this represented all the possible inputs I want to have an approximation guarantee for. So obviously, I mean, hopefully, and obviously it does happen, the size of the number of inputs is the number of inputs increases, the diameter of my compact set increases, so does the depth and width, so the model complexity increases, and vice versa. Small, if I want to have guarantees for like 2 or 3 points, then I'll have a very small network. And then the last thing is the thing I mentioned about regularity. If my target function is smooth or smooth trace class, or if it's holder or holder trace class, if it's super regular, then I'll need a very small network. I don't need much complexity to get it. And if it's irregular, then of course opposite happens. So in other words, our quantitative estimates are first telling us that the things you expect to happen do happen, right? But the second thing is optimality guarantee, is that at least for the finite dimensional setting, when E and B are finite dimensional linear metric spaces, then we achieve the optimal DC type rates. So our construction is optimal. So it's not only universal, it's really as good as you can do, at least in this case. Yeah. Right. And now let me quickly go through the second part of the construction, right? So here I just told you how those neural filters work. That's the object that takes one random variable and sort of computes the conditional expectation in this example, but of course much more general. But now how do you assemble them into our main neural network model, which, let me give you the name. It's called causal neural operator because it's the neural operator and it's causal, that's kind of the main point. Right, so that's this object that takes, in our example, takes x0 and gives you conditional expectation, uses the hypernetwork to update to what that neural filter should look like the next time, then takes x1, gives you conditional expectation, and so on, so on, so on, right? So how do you construct, oh, yeah, the text is blocking side of it. So how do you construct the CNO? So our second theorem, instead of giving you just the theorem statement, there's actually something even nicer coming out, is it gives you an idealized algorithm for constructing the CNO. So given a causal map, so just for pure notational simplicity, you don't need this. I'm just going to take a product of the same space with itself, and that's a sequence in E, and gives you a sequence in B for simplicity, but you can do product spaces. And given an encoding error and some certain hyperparameters. There's an algorithm which does the following thing. Because in step one, you fix some things. The first thing you fix is the number of viable time steps you can make a prediction for before it degrades. And this is with those specified errors, approximation and encoding errors. Yeah, and that's it. And the second thing is how much memory I need to know. So if my function f, which maybe can have long-term memory, if I know how persistent this memory is on the past, then how much memory do I need to achieve epsilon a approximation quality? So that's the second thing it fixes. These are all. This is a nice thing about quantitative theorems to tell you all these things, and then some technical detail about initializing parameters. Now the most important thing is the next step of the algorithm. It says you can do the following thing. Okay, it tells you how to sort of train the causal neural operator. And the key thing from a practical perspective here is that it's very different than recurrent neural networks, right? So recurrent neural networks, everyone knows about them, residual neural networks and these types of things. They're very classical and intuitive object, but they kind of fallen out of fashion recently in sequential prediction, time series prediction, especially in natural language processing, which is a form of time series analysis, because they suffer from a numerical instability problem. Namely, when you train them, your gradients you're doing when you're doing a gradient descent can either stagnate or explode, and so your models either don't train or give you nonsense, right? So this type of numerical instability kind of led another class of models, so-called transformer networks, to overtake them, because one of the main reasons is because the transformer networks are non-recursive, right? But the problem is that non-recursion is not a good thing. It's just non-recursion during training is a good thing, right? So the nice thing about our construction is that you can train it using a sort of federated learning algorithm. And the second step, which is the main step of the algorithm, you don't spend time on initializations, is that. So what happens is you do it like this. You get all the time steps ahead which you want to predict for, now, tomorrow, day after, and so on, up to 10,000 days in the future, whatever. As long as you have that many computers, you can train a neural filter independently on each of these computers in parallel. Okay? They don't talk to each other. There's no recursion. They do their own thing. They become experts on their moment in time. Then the parameters are given back to the central server. It's called in this type of literature, central computer. And this is a really, really simple, the most classic problem possible. It just trains the hypernetwork to predict the vector parameters at every time step with the shifted vectors of parameters. This is a sum of square regression, like linear regression with a feed-forward network, right? So this is it's a federated learning algorithm. There's no recursion amongst anything, but the model that we get in the end, which is ultimately recursive because the hypernetwork is giving a higher order recursion of this parameter space. So in other words, we can get an N-type model which has all the benefits of a transformer network. Cool. And yeah, that's basically what I just told you. So there's a bridge theory. Let me just say that in the work, there's theoretical guarantees for the algorithm I just gave you. The algorithm I just gave you is actually, in some sense, is a stencil of the proof that we use. And there's some guarantees for it, but those are rather technical for, I think, for the slides. The last thing I want to mention is about optimality again. Great. So this is the following thing, is that, so ReLU neural networks were optimal when making finite dimensional predictions, but we can do better. And somehow this is somewhat obvious for a practitioner. Practitioners know, anyone really, by practitioner I mean anyone who's implemented a couple of neural networks in their life will realize that a recurrent neural network for sequential prediction task will do better than a massive feed-forward network. It's kind of obvious, but like, our theory also says that it's the case. So our theory says the following thing. So if you're trying to predict a function which has causal structure using a large ReLU network, just infinite dimensions for this illustrative purpose, but then you consider a CNO, so one of our operators, causal neural operator, even in the finite dimensional setting, then the complexity of that operator, the number of parameters you need to define it, is much lower. It's almost a polynomial number of time steps, whereas the feed-forward neural network is going to be exponential somehow in its error, right? So here, our model is going to be polynomial in the error, and a feed-forward network would be exponential in the error. And so the point here is that if you have a causal structure, you can not only exploit it numerically, but theoretically, you can validate the fact that your sort of recurrent model does exponentially better than a large feed-forward model. So in other words, you get super optimality if you have causal maps. So you should use the causal normal operator because it's great. So it bypasses the VC optimal rate because you know a bit more about the target function structure. Okay, so for the second part of the talk, it'll be quick because we introduce a lot of the ideas in some sense. So yeah, so now we're going to talk about this intersection between geometric deep learning and sequential learning models, right? Okay, so for this one, I want to return to our second problem and just motivate it, right? Because I think this area needs a bit more motivation. But then once you see it, you'll be like, yeah, I'll never do anything else in my life. So the problem is the following: it's very classical, simple math finance problem, the simplest. So I want to it's the most classical. I want to price many path-dependent options on a large portfolio without assuming anything of the underlying dynamics, right? So in other words, I want to compute many of these conditional expectations. Vk are the values of my like the payoff of my options. You know, suppose these could depend on the past. I don't really care. The only thing I want to say is that I want to understand the value of this option for some discounted payoff under some risk neutral measure, which I'm going to assume that exists right now, for some stochastic process xt, which I don't know. I just know it has a risk neutral measure. Given that I've observed at the current state right now is x0 is some value x, right? Okay, I want to compute this vector of prices. No problem. Let's use a classical neural network. Yeah, it's very easy to check that this satisfies the regularity requirements for some L2 type universal approximation theorem. And so, okay, I can approximate the neural network and I can do it very efficiently. Great. But what's the problem? Right, so input is the current state of the market and output is the vector of the prices of all these options. The problem is that, you know, I think marketing this as machine learning is true, but it's also a bit deceptive because you haven't learned anything. You've learned how to price very specific options. You don't know how the process xt is evolving, right? So what have you learned? You learned some stuff. You haven't learned how you didn't learn much about this xt's behavior. So to like motivate this geometric deep learning stuff and to solve this problem, I consider going back to the basics. So forget about these indices and just look at one of these conditional expectations. What is this? This is, you can view it as the usual definition of conditional expectation, or you can think of it in another way, which is integration against the regular conditional distribution of my stochastic process, which I write x now. Condition on the current state of x is little x, right? This is how you teach it, but it's actually a bit harder to define, ironically, right? So the point is that if I can approximately implement this regular conditional distribution, right, the function that takes my current state and gives me the conditional law of my process given the current state, then I can Monte Carlo this for any option price I want. Of course, this is independent of recursive dimensionality, no problem, super efficient as you'd like. So that's pricing is not a problem, but also in so doing, I've learned about the evolution of my stochastic process. I know its law, it's conditional law, so I know a lot about it. Whereas here, I know pretty much nothing, in my opinion. Objectively, you know very little. So in this case, I want to model a function which is taking inputs in Euclidean space, the current value asset, and outputs in the space of probability measures. So d-dimensional space where my process lives, but say for the next t+1 time steps. So the current time step and t in the future. And I'm going to write this regular conditional distribution as just pi x underscore dot worm, which is the input. Okay. So what do I want about this approximation? Like I've said a billion times in the talk, so I'll say quickly, I want it to be causal, yeah. But I also want it to be adapted. And so what do I mean by this? So here, you notice that the output is a probability measure, okay? But if I want to use that thing in mathematical finance, right, I need that's my approximation of pi, because I'm not going to get pi. I'm going to get something close to it. And so when I evaluate pi at x, I have a probability measure here on this path space. And my model is also going to be living a probability measure on this path space. And I want that if those things are close, then they should be good for math finance. And what I mean by this is the first point, it's maybe more obvious, is that if I price an option like the ones I showed you in the past slide, then if my model is close to the ground truth, then the prices should also be close. Okay, that's completely reasonable. The second thing is a bit more subtle, is that if my model is close, I want it to be so that if my model is close to the actual target function, this measure value function, this regular conditional distribution, I want also that the optimal stopping value under my model is close to the optimal stopping value under the true distribution, right? So of course, to care about this, the easiest example is American options, but there's a ton of other examples. So what this means is that, well, I'll show you in the next slide, I want to have a specific metric on this space that will encode these things, so-called adapted Wasserstein distance, and I'll get to that in a second, right? And the second thing I want to emphasize here is that point 2 is for a specific x. I've conditioned on x, and I input an x to my model. Those are probability measures. I don't care about only a measure, I care about measure-valued functions. So I want, for example, uniform guarantees for simplicity, say for all x in the cube, right? So I want these things to hold uniformly for all potential current states in my price process, right? So, okay, so how do we describe a condition 1 and 2, but especially 2 mathematically? Well, thanks to this adapted optimal transport literature, or causal optimal transport literature, it's like this. So, okay, so when you consider the distance between 2 probability measures on our d times t, or t plus 1, sorry, where the output of our model lives and where the conditional law of our process lives, well, you can measure their distance in different ways, and one way is the Wasserstein distance. The Wasserstein distance is a great candidate because if their models are, so if those 2 measures are close and adapted Wasserstein distance, then pricing for Lipschitz payoffs are also close. This is almost by different, the classical stuff is by duality. Great, but it's not true that if my probability distribution condition, like my model with input x is close to the process condition on x, if those things are close, in Wasserstein distance, it's not true that the value of an optimal payoff, of an optimal solving problem is going to be in any way close. So how do we fix that? Well, it's very nice. You can simply modify, well, simply by modifying the notion. So this is if I'm minimizing this distance for all possible couplings. So these are joint distributions on that has my model a condition on x and the true law condition on x as marginals, right? So if I minimize all those possible sort of transport plans or couplings, that would be the Wasserstein distance. But I essentially the problem that's happening with optimal stopping problems is somehow just at a high level. The problem is that there's the Wasserstein distance allows you to transport information back through time, right? Because here they're not just 2 probability measures, they're probability measures with a causal structure. They're on a path space, right? And breaking this causality is actually breaking the sort of the stability with respect to optimal stopping. So if you constrain all the possible couplings of these 2 distributions, so that they're sort of only when I'm transporting mass from my model to my target distribution and vice versa, they're only allowed to transport mass forward in time. So this is called bicausal couplings. I put the formal definition here. Then it turns out that this defines a distance. The distance, of course, obviously stronger than the Wasserstein distance. But the most interesting thing is that if you're close with respect to this stronger distance, then you're also stable with respect to optimal stopping. So in other words, they're good for math finance in both the previous senses. Good. Okay, and the last thing I want to assume, and just very quickly, so I'm going to flash through a slide because of the first part of the talk. I'm just going to assume that the target function, this regular conditional distribution, is continuous. Okay, so yeah, so this point I'll just skip briefly in the interest of time. Now, I rather spend time in thinking about why the continuous assumption is completely reasonable. Well, if you consider any classic stochastic differential equation, then this map is continuous. This is sort of classical stability of SDs. Yeah, so that satisfies our assumptions. In other words, when we do our analysis, all classical SD models automatically are viable candidates for an unknown dynamics of X. But using a sort of a more computer science-y type mentality, by a Lucent theorem type argument, a couple lines, any stochastic, well, almost a couple lines, any stochastic process in this discrete time setting with on a set of high probability, so for a certain set of inputs that have arbitrary high probability, on that set, it's continuous, right? So if you're allowed to get rid of some bad parts and say those have low probability. So there's some bad points in the cube, which are my viable inputs. Then any process will satisfy my assumption, but with high probability. So in other words, either with certainty or with high probability, my assumption is somehow generic. Right? So I want to then approximate any regular conditional distribution which is continuous. In other words, I do a bit more math in the last few minutes. So I want a dense subset of the space of continuous functions from my compact subset of my Euclidean space, which I now call X, into this space of probability measures. Now notice this is obviously not a linear space, which I'll mention in a second. Metrized, so with metric is the adapted Vashtan distance, which I just described, right? I'll just mention it. Clearly, this is not a vector space because if you add two probability distributions, you have mass more than one, right? So clearly, this is what I mean by this is what I meant by non-vectorial structure. This in some sense is a very simple but very complicated example. It's an infinite dimensional object that isn't linear, so cannot be tackled by the stuff in the first part of this slide. Sorry. Right. Okay, so now conceptual stuff. So how do we tackle this problem? Because the approach of part A really relied on these basis representations, right? You had a basis, you truncated the basis of things, you looked at the coefficients, and you transformed the coefficients. Super intuitive, but doesn't apply here. There's no basis, obviously, if it's not linear. So what can we do? So the inspiration that we get is, in a series of papers, actually, is looking at transformer networks, right? So transformer networks are like a great thing from NLP, so natural language processing especially, so generally more importantly in time series analysis, and they kind of change the name of the game over there. So what is, besides this non-recursion stuff, which I described in the first part of the talk, what is another key mechanism, pun intended, of transformer networks? And the key mechanism is a so-called attention mechanism. And what is that? In a slight simplified way, just getting rid of subparameters so it can make the analysis a bit easier. But of course, it holds more parameters. Attention is the following thing. So introduced somewhat recently, it's the following thing. So I call it attention. It takes, you might call it tensor, but just think of it as n points in RD, classical attention. So y1, y2, yn, and a weight is in Rn. And then it tells you how much attention you want to pay to each of these points. So in other words, you're just taking, so the blue part is taking my weight W, it's renormalizing it to the simplex, so the weights add up to 1, and then it's looking at the convex combination of these guys, right? So if the first weight is very big, once you renormalize, that means you want to pay a lot of attention to y1, so your output of attentions could be roughly y1. If, say, the first two are very big and similar, then you'll be roughly a half, half plus y1 plus half plus y2, so then you want to pay equal attention to those, and you get, of course, a barrier center, the mean between those two, and so on. So that's basically the second main ingredient of transformer networks, this attention network, this attention mechanism. So the question is, how can we translate this to our setting and leverage it? So in a sequence of 2 papers, or 3 papers, depending, so advertisement, one of the papers is with very minor revisions in math finance, going to appear soon, special issue on machine learning finance. Guess what? Other one got spotlight at ICLR, so this is like the top machine learning conference, gonna have an award, yay. And there's another paper with some in constructive approximation right now, also some minor revisions. So the point is, like, the math and the computer science both agree this is a good idea. So what's the idea? So the idea is this. Okay, so instead of using a softmax function, we're just going to use a projection onto the simplex. This is just technical, but I want to get out of the way right away. You just want to take your weights, make sure on the simplex, and you want to get that boundary, because in high dimensions that might be problematic. Okay, but if you like, just consider the softmax function. That also works. So blue goes with the blue. The main difference here is the purple. So here we were looking at convex combinations of points in RD, n points in RD. Here we're going to look at convex combinations of n different empirical measures on RD, right? So same idea. So if the attention is saying you should pay different attention to points, the probabilistic attention, or the geometric attention in the more general form, which I'm not going to get into, says that you want to pay different attention to different empirical probability measures. And why we care about empirical? It's because these are implementable in the computer, whereas general probability measures, of course, aren't, and therefore we don't care. And you can't see this because of the, okay, now you can, because of this thing. I'm just going to skim over it quickly. There's also an adapted notion of these empirical measures. I write it down, but I really refer to the paper. It's rather technical. But the point is just that empirical measures can approximate every just measure in Vashline distance, adapted empirical measures are their adapted counterpart. They can approximate any measure in adapted Vashline sense. Okay, so there we go. So here, just for sake of time, just replace this by empirical measure in our minds, but in the paper it's the adapted version, right? So let me just quickly visualize the adapted attention. So it's just taking, once you renormalize, so forgetting this projection, you're taking weights in the simplex, and this is the Wasserstein space. It has a certain curvature, to be honest, and so you're inscribing this simplex into this Wasserstein space, right? So attention is just really just making this sort of nonlinear inscription, right? And so, yeah, so when you're paying a lot of attention here, you're really just moving your output of your neural network, you'll see in a moment, around this point in our high-dimensional nonlinear space, infinite-dimensional linear space. So what we want, how do you approximate this conditional expectation? Well, we're going to call this a geometric transformer. In the paper, it's called metric transformer, but in the revision in about 1 week, it's going to be called geometric transformer because people said it makes more, it sounds nicer, so okay. So how does that work? Well, here is, I have to stop talking so you can see it. Yeah, okay, the captions are there. So that way, it's also very similar to before, but slightly different. So the inputs, remember they're Euclidean space, so we got rid of the first layer. It is a feed-forward network. Transforms the inputs to some kind of, as we call it, latent code, as you call it, some abstract vector. And then that is just passed to the attention that I just described in the previous slide. So it takes that, it projects them, so we get some weights onto the simplex, and then takes convex combinations of some specific empirical measures, which you can train, and RD. Okay? And then let's sum up the talk by saying the following thing. Well, we have qualitative approximation guarantees for this, right? So given any good activation function, doesn't have to be the ReLU, but I'm just going to wrap up with a bit more generality at the end. So given a good activation function, any compact set of inputs in RD, which I care about, and a continuous function, any continuous regular conditional distribution to this adapted Wasserstein space, any approximation error. Notice there's no dimension reduction error. There's only an approximation error in this case. There's a transformer. There's a probabilistic transformer, or this geometric transformer in the general paper, sequence of papers, that gives you a uniform control of the adapted Wasserstein distance. So that means that when I take my conditional distribution, which I want to approximate, and I condition on any input in my compact set X, and I evaluate my model of the same input, then the adapted Wasserstein distance is at most epsilon. That means that, yeah, that whatever is happening in the real world, as soon as I'm conditioning on what happened, like what's currently observed is little x, then I know that no matter what, my approximation of the target regular conditional distribution is no worse than epsilon. Of course, it could be much better. And in adapted Wasserstein distance. So the consequence, this means that, of course, we can then do two things. First thing, we can, once that's epsilon close, you can, of course, price all these Lipschitz chaos functions, and automatically that means we can also use our model as a surrogate viably for optimal stopping problems too. So great. Right, and just like before, I'm just going to put this here. We have quantitative versions of our results, and those say the same things before. The model is more complex or less complex depending on how many inputs you want to process, on the approximation quality, and on the regularity of the target function, in this case the regular conditional distribution. But there's also one more component, the dimension reduction bit. It gets, we can write it explicitly in this case, so as a function of epsilon. And for those who are familiar in the quantization of measure literature, you'll notice that without assuming anything about xt further than this, this is the optimal quantization rate. So somehow we also achieve optimality again, but now in our measure valued approximation type approach. Right, so you compare, yeah, so just to reiterate, let's have a couple of minutes. Yeah, when I assume to do Monte Carlo against, so once I've trained my model and it's epsilon close and adapted Wasserstein distance, and I consider payoff, this payoff has a certain Lipschitz constant, m, okay, that's given to me, epsilon is also given to me because I've trained my model. Then I can, of course, automatically do Monte Carlo and get arbitrarily good approximations of my whatever payoff I want to get. Likewise for the optimal stopping problem. So, yeah. So let me just flash quickly to this. Why would we want, like, how do we now build the same idea before, like the analog of the previous idea into this setting? So now I'm going to open up the hypernetwork a bit more and look inside. So the causal neural operator in our setting is, in this geometric deep learning setting, is what we give the name the hyper transformer, or yeah, hyper transformer, hypermetric transformer. Sorry, geometric hyper transformer, right? So how does it work? It's quite nice. So there's one special difference from before. So remember, at every single time step, we were previously we were taking a part of the sequence and producing the input sequence and producing something from the output sequence, then updating the internal parameters of our model and going on. The difference here is that here we have we can do something which you see often in we see all the time, I guess, in transformer networks, which is you can split the network into an encoder-decoder part further. So what happens here is that you have the probabilistic transformer, which I just described in the previous slide. This is somehow a fixed decoder, and the part that changes through all time is just a regular feed-forward network. So what it does is it takes truncated part of the time series, the feed-forward network processes it, gives you some abstract latent code, so just some vectors, Euclidean space, and this is passed to a probabilistic transformer, and the prediction then comes out, it's a probability measure. The hypernetwork then makes an update. It doesn't make an update on the entire parameter space. Rather, it's much more efficient and it only makes an update on this encoder part of the network, because the role of the encoder is just to tell you how to transform time series into something you can process into, conditional distributions. So the hypernetwork then is this dynamical system on the parameter space, but only on the first part, on this forward part, and makes updates. Next part of the time series, then next time series segment comes in from x, say t+1, all the way back to some very distant past. This process displays some code and it's passed the same probabilistic transformer network to make a prediction and so on. And you keep going and you get the guarantees. And just as one more picture, because I think with this math now it's time to cool down with some pictures. What I showed you is like this. So here on the bottom we have the probabilistic transformer. I use some color coding to show that these units are all the same for all time. And here we have the hypernetwork blocks. These are updating through time. They're color synchronized with this guy here. And the hypernetwork is just the arrow that's going, it's the dynamical system that's going forward in time, updating our parameters. So the way it works is exactly that. It's exactly, just to visualize it, I think, you see the time series comes in. The hypernetwork then produces a law for, say, the next 10 steps or whatever of your process. Then more time series comes in. And then again, you produce another law with the updated parameters and so on, right? And the color coding means that you've updated your internal parameters of your network in the process. So bridge theory, all the analogous results to the linear case hold. Again, you get super optimal rates, and you can even get even better if you're, just for curiosity, using discontinuous functions. Now, how to train those, you might consider some randomized procedure, but that's for future research. But at least you know you can do even much better like that. And yeah, so here I used adaptive Wasserstein space as an example. A lot of times you can assume more structure of the process which you're approximating. Yeah, so for the simplest example, the most boring example, but quite nice, is conditionally Gaussian or something. Anyways, in many of those cases, the framework, the construction I just presented you was a very, very special case of a very general framework that can be customized to almost any geometry you can imagine. So really, I'm presenting to you here, and in both parts of the talk, and especially the second part, is a super general geometric deep learning framework that says this. You give me some structure in my math finance problem that I care about. In this example, it was probability measures that are stable with respect to optimal stopping. And then I'll give you a model that's optimal for that type of design. It preserves those types of geometries, right? So always jumping ahead of myself. And the conclusion is, conclusion from top to bottom was this. So several mathematical finance problems are defined by their structures and specifically by causal maps. Several, of course, some may not be, but most, at least in discrete time, yeah, for sure. And yeah, many of the geometries of creating in robust finance are not compatible with classical deep learning models, right? Those geometries they may be linear, infinite dimensional geometries with causality, or in the second part of the talk, there may be some nonlinear geometries that are especially appearing when you want to predict probability measures or conditional loss. Okay. That's the motivation. And the solutions were, well, in both cases, with linear and nonlinear, or linear if you will, and geometric deep learning, we proposed causal deep learning or causal geometric deep learning, respectively, frameworks which are compatible with these types of geometries from mathematical finance. We derived universal approximation guarantees for these models. So that means when you go home, you plug in that model. If you like the talk, you know it's going to work. And you know, third point, that somehow these are as efficient as possible as you can possibly hope in this context with a number of parameters. And the last point, which I'll read off my slide. Yeah, I can't read it. Sorry, anticlimactic end. Okay, here. Yeah, so, okay, right. So the last point, okay, as usual, I already said it. These models are super optimal when approximating causal maps in finite dimensions. So it's, yeah. So if you notice a bit more structure, like you typically, like have clearly motivated, you have some causality structure, then this architecture is, or this type of framework rather, is better than you can do with a feed-forward type model. And let me just say in the last minute before I take a question, that of course these are theoretical foundations using the simplest possible model as a prototype, the feed-forward network that we then put into our frame, like our approximating or deep learning framework. But of course, I think it's really interesting. I'd love to hear about it. So if you try any other model, you can of course do other things. You can put convolutional as your sort of modular part in those constructions. Please do so. Please try it out, and honestly, let me know how it goes. Now, the last thing, everyone likes to advertise, so I'm going to advertise. I just started a professorship at McMaster University, and I already have a PhD student and a postdoc. Yay! I'm never sleeping apparently. I'm looking for others. So if anyone's interested, yeah, just apply and reach out to me. Cool. So thanks.
Okay, thank you. Do we have any questions?